Okay, so let's start walking through the implementation of SimCLR itself, right? So first, we're going to define a Lightning module, right? So here, we could do it in a few ways, but we're going to do it this way. We're going to define the code itself inside the Lightning module, right? So normally you would have nm.module, right? But in this case, we're just using Lightning, so we're going to do Lightning module. And it behaves exactly the same way as an nm module, except we give you more methods, right? So here we're gonna need a few parameters. So first is the batch size. So we're gonna include that in here. The number of samples that we're dealing with, and this is really for all of the learning rate stuff.
Yeah.
And then world size, and we'll set that to 1 because this particular machine, I have one GPU that we're gonna be using. And then we want to warm up, right? So we have epochs that we want to warm up for. So let's just say we want to warm up for 10 epochs, and then we want to train for a max of 100 epochs. And all of these values come from the paper, the SimCLR paper. And then we're going to set the learning rate of Lars as well here. So let's call it 0.1 initially. And then the Lars ETA parameter as well. So we'll set that to 1 E -3.
You might see, you might see Lars ETA as also as trust coefficient in some other places or some other implementation of Lars.
Yeah, good point. And then we have the weight decay value, right? Optional. Sorry, this is for the optimizer.
Yeah, optimize decay.
So we'll set that to 1 E -6. And then there's the loss temperature parameter, which we described as tau in the loss function. So for every similarity, we divide it by tau. So this is what we're setting it as. It's just going to be a constant here. And let's just make this look a little bit nicer. So we'll split this up a bit. Okay. So now we have to, standard Python. So we want to init our superclass to make sure we get all that functionality. And now, I could do this. I could say batch size equals batch size, and then self dot num samples equals num samples. But that's kind of annoying when you have a lot of stuff. So in Lightning, we have a trick. You can just call this. So save hyper parameters. And then that's also going to save them to the checkpoint. So automatically pulls all the signature stuff here. So all of this stuff will be automatically saved. But also I can access anything up there now by doing the save h params and then batch size. And so now that works. So I'm going to use this as a trick to save me some code. What was that?
Yeah, so I would say this is one of the most useful features in Lightning that I've found.
Yeah. And so here's the loss, right? So we're going to we already defined the loss in a few previous cells up here. So we're just going to import that directly. So we're just going to tie that up. And then as an encoder, like we said, we can use any encoder, but we're going to use a ResNet 50 because that's a pretty standard encoder. That's not going to break the bank when we train this thing. And then the projection layer here. So that's, this is going to map that H is going to go through those 2 lines. And then the output of that is going to be Z, right? So that's what this is doing. And then now, specifically, we're doing CFAR10 because we want to train this in a reasonable time. If we were doing ImageNet, we wouldn't do what we're about to do now. But this encoder, the outputs, the first convolutional layer is not really designed for CFAR10, so we just want to adjust that a bit. So we're going to make that conv work for CFAR10. So we're just going to replace the first layer here.
So the original ResNet 50 has a kernel size of 7 and a stride of 2 in the first convolution layer. That really brings down the ImageNet size, like ImageNet image sizes from 224 cross 224 to a reasonable amount. But CFAR10 is just, 32 cross 32. So you just replace that.
Okay, and then the final thing is we have to add a max pooling layer.
So we actually modify the original max pool layer of a ResNet 50. So instead of having a kernel size of 2 and a stride of 2, you simply change it to 1,1. So that's equivalent to removing the max pool, the first max pool in a standard ResNet 50.
Let's configure the optimizers, right? So that's kind of like a lot of work in SimCLR. So there are a lot of details there. So let's just knock that out real quick.
Yeah.
So one thing about Lightning that I like is that there's no guesswork about what optimizers, what tricks people use. Every method is just tied automatically with like all the details of how they did all the tricks with the optimizers, right? So in this particular case, the first trick that they do is that they actually ignore certain parameters, right? So we are going to ignore from the weight decay all our parameters. And that function, I'm just going to copy paste here and then kind of walk through, right? So we want to ignore these parameters here. Okay. So from the weight decay, we have the parameters, we have the weight decay, and then we're going to ignore the batch norm and then the bias layers, right? So we're going to look through all of the parameters that we have in our model here. So the encoder, projection, all this stuff. And then we are going to just say, for all the biases and batch norms, don't apply weight decay to them. Do you want to talk about why that's necessary?
So, okay, so the reason we do that is the batch norm or the bias parameter just, so if you have a n-dimensional hyperplane, or the simplest case is y equals to mx plus a, it's just one dimension, the bias is literally controlling the shift of your line. And that's why you don't want to constrain that using an L2 regularization. The same thing in case of batch normalization. So the batch normalization parameters control your scale and shift of the output of the batch norm layer. And hence you don't want to restrict those scale and shift values.
And now we're going to do the optimizer, right? So in this case, we're going to use Lars, right? So you could, it's kind of like hit or miss on this, but well, anecdotally, it sounds like Atom and the other optimizers may work just as well, but I don't think there've been like super strong ablations done on Lars versus Atom versus whatever for these particular methods. So I think people are using Lars mostly just because that's what they know works. And since these things are pretty expensive, they take, a lot of compute to train. It's a little bit hard to sit here and like grid search all the possible hyperparameters all the possible optimizers you could use. Yeah. So we're just going to keep that trend and say, we're going to use Lars. This Lars comes from bolts, right? So there are many implementations. You can use your own, but we have an implementation of it in bolts. So you can just say from bolts, optimizers, import Lars. So the parameters we're going to optimize are these filtered parameters, right? So they don't include the bias or the batch norm. And we're going to set up a learning rate. And remember, we called this function here, which saved all of these arguments into something called hparam. So we can just bring that out. And then we'll call that learning rate. Actually, we called that lars.lr, right? So that is this guy here. Let's separate this to make this clearer. Okay, so that's the Lars learning rate. And then we also have the ETA parameter, which we also pulled from the hparams. So this is Lars ETA. Okay. And now we need to do, so we'll call this trick one, right? Trick one, use Lars plus filter weights.
So after the optimizer, we define our scheduler, and we had a fixed number of epochs for which we wanted to do a linear warm-up. And we are using the scheduler after each step instead of each epoch, and hence we multiply the warm-up epochs by the number of iterations per epoch here.
Yeah, so every time training step gets called, that's where we're going to update the learning rate, not at the end of one whole loop through the batch, through the training data. So then we have this linear warm-up here, which I'm just going to paste. And
yeah, that's your scheduler right there.
Right. So this is also coming from bolts. And can you explain how this scheduler works?
So this scheduler just like takes these values, warm-up epochs, max epochs, and like a start learning rate and a final learning rate, that is the ETML. It starts from this warm-up, the warm-up start learning rate, goes to the maximum learning rate of the optimizer in the number of epochs specified for warm-up, and then does a cosine decay for the remaining of the remainder of the epochs. And since we are doing this for each step, we'll just define how that works in PyTorch Lightning. So you can simply use a simple dictionary to call this scheduler for each step.
By default, Lightning update schedulers every epoch, but you can override that by specifying this. And you can also change the frequency of how you do it. So in this case, if you wanted to update every 10 steps, you could do this, right? But in this case, we want to update every single step, and then we're going to pass in the scheduler here. And then in Lightning, you're just going to now return the optimizer and then the scheduler as well.
Yeah.
And the reason why it's an array for each one is because you could have multiple optimizers, right? For like GANs or something like that. So each one could have its own scheduler or not. So in this case, we're just using one optimizer and one scheduler. Okay, so we're done with kind of the optimizer part of this. So now we want to, so we use this value here, trained iters per epoch. And we need to, since we want to make our code reusable so that we can work on any number of GPUs or TPU cores or whatever you want, then we need to actually calculate this number after some setup has been done and like the model is kind of alive and we know the world size as well, right? So the world size refers to how many GPUs and nodes you're training with. So we can do that in this function called setup, right? So setup will be called once the whole distributed system has already been set up. So on each particular GPU in the model, it will call setup on that model. So you'll get past this stage argument, which stage can be fit or test, right? So if setup happens when you call .fit or when you call .test, then it'll call this particular argument. So first, we want to adjust our batch size. So we're just gonna calculate like the global batch size, right? So we're saying, okay, give me the whole world size and then the batch size for each GPU, and then that's going to tell me the whole batch size for all the GPUs I'm training on. Again, if you were to call this somewhere like init, for example, well, distributed hasn't been set up yet because the model has just been started, so you wouldn't get that information then. So you have to do it here. So once you do that, then we're going to take the number of samples that we have in our data set, and we're going to just divide that by the global batch size, and that's going to give me how many iterations we're going to do per epoch. So we set that up in the setup call here. Okay, great. So now we get into the meat of the training, right? So we're done kind of setting up all the boilerplate stuff that you need for SimCLR. Now let's do the actual training itself. So we're going to implement the training step. This is at the heart of what's happening. And in this case, we're using only one optimizer. So the arguments that we're going to be passed in are these. If we're using multiple, we would also be passed in an optimizer index here. So we could say, is it 1 or 0, whatever. In this case, it's just the 1. So again, here we're first going to get the image, right? So we got two images, two versions of an image. And then we have labels, which we're not using right now because we're training on supervised. So we're dropping these labels, but we're going to keep them around for a second. So we get these two images. And so the first thing we need to do for each image is that we have to encode it, right? So we have to create the H for each one of them. So we have the encoder that we defined. We're going to run that image through there. And in Boltz, we've modified the Torch Vision RESTnet to have an option where they can return the outputs of every single layer. And that's because a lot of contrastive learning approaches, or some of them, use that. They use that information, right? So we just want the last one in this case. So we're just going to say just the last one. And then, so just to be clear, what would happen in the RESTnet normally is that you would have something, so I'm just going to divert for a second here. So you would have something like x equals, call it RESTnet block, RESTnet block 1, and you get x. So you get this x1. Let's just say that you have 3 blocks in this RESTnet. So we're going to actually track the outputs of each block, right? So 3 blocks, and then you get the output of 1, which is x1, and this is x2. And then in Boltz, we return actually all of them. So x1, x2, x3. And since I only want x3, then we're just going to do -1 here.
So in case of a ResNet 50, this is the output of the 5th convolution layer.
And now this is for image 1. We need to do the same thing for image 2. So we're just going to run that again. So image 2, and we're going to get the second H, right? So this is the encode, and you build these kind of representations, right? What's happening here is you're going from batch, and it's going to be like 3 by what were this?
So for CFAR10, I think it's 2 cross. Oh no, so the input.
Yes, 32 by 32, no?
Yeah.
Yeah, and then that's going to be mapped to batch by
2048.
what is it, 2048?
Yeah, 2048. Comma 2, comma 2.
Yeah. So it's just the output.
Yeah.
And now we're going to project those, right? So we're going to run this through our projection head, and that's going to give a Z. So remember the projection was H, so we have image, and then we run it through encoder, and that gave us H, and then we run that through this projection head here, which we had 2 lines for in our slides, and then we get the Z. So this is that Z that we're getting. So that's self.projection, and we're going to pass in H1, and then we're going to do the same thing for the other image as well. So H2. So again, you gotta mentally, you have to think about it as 2 streams where you have one version of each image going through each stream. And then at the end, you're going to do something with those versions. So that's going to map from batch of 2048 by 2 by 2 to batch by
128.
128. So a single vector that summarizes that whole image. Okay, so that's the projection part, right? So this is encode. We'll call this project. And now we need to calculate the loss, right? So our loss, as we said, we took it for granted that we were getting the correct inputs here, right? So we're getting the Z1, Z2 here. So we're just gonna go ahead and pass that. So now that we have our loss, we can just call it, where's my loss here? Here. So pass the loss, and then that's going to take in Z1 and Z2, and I have a typo here, Z2, great. And I believe we'll also need to pass in the temperature. So and that's what you're dividing each element by in that loss function. So we pass this in up here as a parameter to our model. So I think something that's super nice about Lightning as well is that like it's self-defined, right? There's no guessing, like what was the parameter that was used, like what are these random numbers floating around. When you define it in your init of that Lightning module, you specifically can set the good default so that people know what the things are. Is it a string? Is it a float? Is it a double? What is it, right?
Yeah.
So that's the loss, and then we're going to return this loss, right? So in the training step, we're just sending back this loss, and this is for a batch of training data. On the validation step, we're going to do exactly the same thing, right? So it's literally the same code. So in this particular case, I could literally copy paste all of this, right? So that's going to give us our validation loss. And then, we can turn this loss here. But the validation step is really there to like, in our particular case, it's mostly just to log, just to see how the training is doing, just to see how we're doing against a held out set of data. So since we're using the exact same code, I'm just going to rename this shared step, right? And it's going to be the same step that we're going to use for anything. And then instead of calling it twice, I'm just going to call here. I'm going to say self.shared step batch index. Right, so it's the same thing now. And then for our validation step, I'm just going to use the same shared step. So validation step.
So what I would like to say here is that anything under validation step would be without grad. So even though they are a shared function, it won't matter.
Yeah, exactly. So by the time your code gets here, Lightning has already called these functions, right? So it's basically like calling this. It's like saying model.eval, and then with torch.noGrad, and then calling here, right? So loss equals model.validation step batch. So it's the same thing. And so it does that automatically for you. And then when it's done with the validation loop, it will put the model back into training here. and then that's it. So that's a good point. Yeah. Okay, so we don't have to worry about stopping gradients or anything else at that point. Okay, so it's the same thing. Now we want to log things, so I don't just want to return the loss. I could just do this and we'll train and it's fine, but I actually I want to log. I want to see the curves of what's happening. So I'm gonna instantiate a result object here. So this is just a dictionary, but it lets us map, it lets us do like convenient functions like log or write or so on. So we want to minimize this loss, right? So this is equivalent to this. So if I were just return this is the same as just doing this. Mm-hmm. So I'm going to not do this one instead. I'm going to do this one. And I want to log. So I want to say, okay, well, let's call this my my train loss, right? So we'll log this and say train loss. And by default, Lightning will do that logging on the training step on every single step. So it's equivalent if you had this for batch in train data, right? Loader. And then here we literally just do all of this. So we got the loss, you know, it's model dot training step, pass in the batch, this. And then normally you'd have like optimizer dots, you'd have like loss dot backward and so on. So Lightning does that part for you automatically. Here, all of this. So you can get rid of this. But more importantly, it can log here, right? So by default, it's going to log here. So it's basically like if you were to do this print train loss, and then you pass in the loss, right? So it's printing there. But I also want to log it at the end of the epoch, right? So what if I wanted to do something like losses equals this? So I would have to track those, right? Append, and then loss. And then I want to log at the end of the epoch, I would just do print losses.mean in pseudocode, right? So it's not going to actually work, but this is what I'm trying to do. So something like epoch train loss here. So it's the same thing. So to do that on Lightning, all I have to do is just set this with a flag here. So on epoch equals true. And then we'll do exactly the same thing.
And I mean, the whole benefit of having the results object is, so if you're doing this for the validation step, so you also have to keep track of, I think, like, no, sorry, not validation, but you also have to do detach gradients and everything before you take the mean of the whole thing, or before you store all those loss values in the list, right? So all that is taken care of within the results object.
Great. So that's our training step. So that's it. You know, it's pretty simple. Now for the validation step, it's the same thing, right? So we can just copy paste all of this stuff again. It's basically the same, except now we do eval result. And the reason we change the name is because the defaults for the eval result are slightly different, right? So on train result, the default is that it'll log on every step. But for validation, it doesn't really make sense to log every single step unless you're doing something like a histogram. What you want to log is the average loss or something over an epoch, not at every single step because they're all independent. So the default logging behavior for here is that on epoch is set to false, right? So this is the same thing here. Instead, sorry, it's set to true by default. Yeah. And by default on step is set to false, right? So if for some reason you didn't want to log like every single step as well, you could set that on to true. But in this case, we're just going to take the default behavior. So we're going to turn this off. So we're going to log this. We'll call this average val loss, right? And it's going to be this. And then here's the other thing about the eval result, right? So it's you can change what you checkpoint or early stop on here. You still have to enable those as callbacks, but the value can now change dynamically, right? So I do want to checkpoint on this loss every single time. And the beauty of doing it here is that like if I had something else like accuracy, for example, and if I was doing something else, then I could checkpoint on the loss, and then maybe tiny bucks in, I change it to accuracy or something else for whatever reason, right? But you could modify that if you wanted to. So we're not going to do early stopping because with contrastive learning and self-supervised learning, you want to train as long as you can, and as long as your compute will let you. So this is going to be our loss. So that's it for this. Okay, now I believe we're ready to go. That is everything we wanted to do. Okay, perfect. So that's it. So notice something. This is an NN module, but I didn't define a forward. And the reason for that is because Lightning defines full systems, right? So you're training all of SimCLR here. Now, if you wanted to use SimCLR for predictions, you could, for inference, you could define a forward, right? So you could do something like this. You get some inputs, and then you decided what you want to do with it. If you just want to use encoder, then you can just do self.encoder and pass in the x, right? And again, I just want the last feature map out of it. So for now, we're going to leave that. We're going to not add this because we're not going to be doing inference anytime soon. We're just training. So this defines all of the SimCLR model. And I'm going to run this. I guess we have an issue. Missing some dots somewhere here and here. Okay, great.